Okay, so for the second part of or second episode, I guess you would say, I'm going to go through the method section. So last section was more the background information. All of you should be doing some background information on your topic, maybe some literature review, understanding the key definitions if it's more of a technical topic like mine was. This picture, I think, is a good diagram to sort of remind you of what I talked about last week. Compartmental models like SIR, or in this case, SEIR. Basically, the idea is you have you start with, let's say, a number of susceptible people, and maybe you introduce a few infected people to some sort of infectious disease. Could be COVID, could be something else. It looks like I have birth and death rate as mu, and we have various parameters. So it looks like you have a transmission rate, you have recovery rate, you have a vaccination rate if there's vaccine available for like there is now for COVID, and you basically you press play. And we did that with, I showed you how to do that with in Excel, or I guess in Google Sheets, spreadsheets. But the problem with the one that I did really quick was, it measured like fractions of people. And it was what we call deterministic. It wasn't calculus, but essentially it was more like a calculus model than a statistics model. Whereas what the purpose of my research was to sort of compare those two. So it's very much related to what we talked about yesterday. We actually talked about theory-based versus simulation-based inferences. So it's very much related. Because, if you have a smaller sample size, so I looked at, a small community of 2,000 people. That's sort of what I placed my focus on. How much of a difference is there in what parameters, what variables have an influence on that? So I'm going to talk about that. And yeah, I think most of you guys are sort of in the methods part of your project. You're figuring out how either you are sending your survey out if you're doing a survey, or maybe you're looking for research online. There's a few different ways you can collect data. So as I mentioned, about half of you are doing survey type stuff, and about half of you are doing, looking for stuff online, reliable sources, that sort of thing, to figure out answers to a research question of some kind. So you started with a research question, and now you're trying to collect data to answer that research question. Hopefully that's where you guys are at the very least. And some of you might be further. That's great. I don't think anyone's doing an experiment, but that's another way you can collect data if it's possible. But none of those are really possible for my research projects because, infectious diseases, you can't do an experiment. Obviously, the ethical issues with that. It's not really a survey, or you guys, you could look at reliable data for your parameters. But in terms of answering a research question, one of the methods, the main method I used was simulation. So I talked a little bit about that last week with the spreadsheet, but simulation, instead of there being a smooth curve, there's a randomness inherent to that. So you might not get that smooth curve. You might get more randomness. You might get these little jaggedy phenomenon, I guess you would say. So these are some histograms of some particular simulations of my sample size, or my population of 2,000. What I did is I started with 2 infected people. I had a reproductive rate of 1.8, reproductive number of 1.8. So remember from last week, if your reproductive number is bigger than 1, your disease will probably grow. If your reproductive number is let's say 2, then the first person infected, you can expect them to infect 2 more people. So it's like exponential growth, at least at first. And I looked at 2 scenarios, one with no vaccine and one with a 7% per day. So a very rigorous vaccine program, much more vigorous than what we're doing, or than what we're able to do. But that's just sort of hypothetical. But it's interesting, if you compare those two, there's a bar on the left that reaches about 35. What happened there was those first 2 people that were infected, we got lucky. They didn't infect anyone else, because in the simulation model, it doesn't say for sure that the first person is going to infect 2 people. They might infect 5 people. They might infect no people. They might infect like a super spreader. There's a randomness inherent to the process. So sometimes you get lucky and nobody else gets infected. But most of the time, or a majority of the time, like 2/3 of the time, the disease spreads, and you get sort of like almost 2/3 or maybe 3/4 of the population sometimes getting infected with this hypothetical disease. Whereas if you vaccinate, you can see on the x-axis the final sizes are much less. Sometimes you still get closer over 100, but most of the time it's between 0 and 100 people get infected, because you might expect that. There's a vaccine program, so 7% per day. So of course, vaccine, not surprisingly, make a huge difference. But what's interesting is that bar on the side is about the same height. So that was one. Now, just to clarify, your methods section actually wouldn't have the histograms or the scatter plots or that sort of thing. That actually goes in the results section. I just wanted to show you like what a visual of a simulation result would look like, I guess. So that's I basically split the method section. If you look at the research paper guidelines, I split the methods into 3 sections, one of them being data collection, the other one being variable creation. So this one I really, I think in most of your comments on Google Classroom, when you submitted your proposal, I really tried to kind of, if the variable wasn't clear, I tried to give you some suggestions in this area. For my research projects, I had many explanatory variables. Don't worry, you only have to do one. Use one at least. You could do more, but some of them were, like, for example, reproductive number that we talked about are 0. Initial infected, as you saw in that little simulation, was at 2 but they could have changed that. Vaccine rate, how effective the vaccine is, and length of the vaccine program, whether or not I ran a simulation, stochastic, or I did like the calculus, the theory-based model. So because I actually compared those two. So I guess that I included that as a variable as well. And so those are the variables that I controlled. Okay, so those are the things that I tweaked before I ran my simulation. What did I measure after my simulation ran? That would be my response variable. Things like total infected, but many of you may be object to the fact that maybe total infected is not the most important thing, but actually peak infection, because you don't want the hospitals to get overloaded. So that peak infection, if we're minimizing that, it may reduce total damage, total deaths, and hospitalizations, or I guess deaths would be minimized if people are able to get their care quicker. So, and then time until eradication. And one that I looked at was sort of that fade out. So whether or not the disease took off or not, like I explained on the previous simulation, like about in the last, those histogram, like 35% or so faded out. And that was a binary response variable. So either it did or it didn't. Those are different things I looked at, and I ran multiple simulations and multiple simulation sets to sort of answer different relationships between these. Don't worry, you only need like one explanatory and one response, and some of you might go a little further than that, depending on what you have, but most of you only have like one of each. And so that's the second thing, variable creation. So collect your data, figure out what your variables actually are, and then how are you going to analyze once you've collected the data and you've got your variables set up. How are you going to analyze those variables? Well, what I did was I looked at, as you mentioned, you saw earlier, I did histograms, but I also did like time series of one specific simulation, or maybe like 5 or 6 different simulations, or just a handful of simulations, to let people get the idea of what an infection curve might look like. So for the visual of the reader, it's helpful to also look at specific simulations. And also histogram that maybe record something like final size or peak size. It could be as well. I think I did final size on the mainly, but you could have easily done other response variables. And then histograms, of course, we studied those. You have like the final size is on the x-axis, and then you have frequency on the y-axis. So it would count like how many of the simulations out of, let's say, 100 or 1,000 were in each category. So histogram, some of you might have histograms, and if you have quantitative variables, you might find histograms helpful to display in this section. I also had, I explained like what percent of I described what percent of the simulations had that fade out effect. In various simulations, I looked at mean, median, and standard deviation of these simulations for various summary statistics. So, and I also looked at, which was sort of the main emphasis of my research, was to look at like, how does the simulation compare to the deterministic model? Okay, so the deterministic model is like the smooth curve, as a reminder. Yours does not have to be that complex as mine. As again, I want to reiterate that, but I want to give you like sort of the backbone of it, like the structure is similar. So it's but what you'll probably do in your project is you'll start with some descriptive statistics. So maybe that's a sample mean, or two sample means if you have two groups that you're comparing. Maybe it's standard deviation. You probably would want, I didn't mention that, you probably want like standard, you want some measure of spread as well. If you have a categorical variables, you want to maybe look at proportions or two-way tables. If you have quantitative variables, histograms might be helpful. If you have two quantitative variables, scatter plot is probably the way to go. If you need help with that, let me know. But you're also going to want to do like inferential statistics that we did this week. So the hypothesis test, 3S strategy, p-values, and then if applicable, confidence intervals. We haven't talked about confidence intervals, but that's a topic for, I think, we'll introduce next week. This is just, I snipped a little part of my research project write-up, just because I thought that you would understand at least something from here, and it's very much related to what we've been studying. But my model, basically, it ran on like 0.1 days is like one step, and I ran it for like 200 days, so 2,000 time steps, because there would be 10 steps per day, and it followed a binomial or multinomial. Multinomial is basically if you have more than two options, for which is the case, so it's very similar. But I use binomial distribution basically to run the simulation. That's something we've actually learned in class. So hopefully you find that somewhat interesting. So I actually used this binomial, which you probably recognize that formula. That's the binomial formula, probability that x equals x, and then you get to choose that little bracket there, n with an x on top. That's just n choose x. It's just another way of saying that. And I also have like a matrix. I'll explain that. So like the first row, if you are susceptible, you have a probability of saying susceptible that's probably pretty high, but there's a small probability that you'll get exposed to the disease. There is also a probability that you will get vaccinated. There's a probability, albeit very small, that you might die. But that's the probabilities are sort of encaptured of going from one state to the other. So if you're exposed, you might be infected. If you're infected, you might recover or you might not. So that one, the infected one would be like a binomial basically. And I think it would be binomial if the death rate was 0, which for a lot of simulations, it was negligible. So I just made it 0. So that would be a binomial, let's say. If you're infected on one time period, there's like a certain % chance that you'll recover, a certain % chance that you will not recover. That's binomial. You can model it as such. So that's kind of cool. Simulation sets, I'll talk a little bit about those. My first couple of simulation sets, I started with initial infections equal to 2. That's like the one I shared, but I also compared that to if we had like a whole bunch of people, like 10 people getting infected at once, and then they're introduced in the population. Aggressive vaccination rates, and I recorded the important statistics that I mentioned before, and I compared the results to sort of that curve model that we talked about last week. And then I looked at the histogram. Those are the ones I showed you. That was for one of the particular scenarios, but I did this for a bunch of scenarios. I did it for 1.8 R0, 1.5, or 1.2. I tweaked the vaccine efficacy for 0.5 or 0.7. And I also looked at no vaccination, how it compared to if you didn't vaccinate it at all. So these are the variables I sort of tweaked. And I looked at time series as well of each of these cases, so you could sort of get the reader can get a sort of a visual of what might happen under various scenarios. So what I actually did is I blew the dust off my master's thesis. I copied it into, it didn't let me copy and paste. I had to like type it out. It didn't take too long. But I typed out the code, made sure it worked. And I'm actually gonna do that. See, I don't have it open. I thought I did. That's right. That's weird. Okay, so I'll just have to find that real quick here. Okay, should be hopefully open. Oh, sorry about that. I thought it was loaded. There's my master's code, and I don't think this thing takes too long. So this is R. R is a helpful tool to run simulations. It's free too, and it's like you can run simulations. You get a lot of statistical analysis on it. So it's a fun little. Even someone like me that doesn't have a huge programming background, I was able to kind of, find my way around when I was doing this. So here we go. So there's my code. Boom, boom, boom. Now I should probably, as this is waiting, I'll explain what the input parameters actually are. So this simulation, it's assuming, I made a little bit of typo. It's actually population of, it's not going to matter too much, of 1,995. I've got 1,900. Oh, wait, I've got about 2,000 people in this small town, and 5 of them are infected. Initially, we have, in this case, I have a vaccination rate of 0.7%, it looks like. So a very small vaccination rate. And vaccine efficacy of 0.7. R0 is about 1.5. It's not explicitly stated in there, but it's actually a formula that relates beta and gamma. And so with those input parameters, let's just see what it turns out. So this is just a various scenario, a specific scenario, and this is what you get. So there was 5 initial people infected. So because there was more people initially infected, you got much less that faded out. But then you kind of, what I noticed was this bell-shaped curve conditioned on that it actually starts. So that's sort of what I noticed a lot, a pattern when I was doing that. So it's either it starts, or either the disease spreads or it doesn't. And if it does spread, it follows like a bell-shaped curve. So that's one of the findings. So that's just show you how you could do it. Another thing you could do is if I do plot, if I go in here and I just say, I tell it to plot I. So it's going to plot my infection. It's going to do it for the last simulation only. Boom. So you could see that kind of looks like a reasonable thing that might happen. On the x-axis is time in tenths of a day. So it's actually 80 days or so that the disease tapers off. And you could see that the peak infection is about 60. So there's no more than 60 people infected at a time. But the actual epidemic size in this case, I could actually figure out what it was for this particular simulation. I'd have to type in A3, let me see here. No, which one is final size? 1. I'd have to go like this, and it will actually tell me. There we go, so 647. So 647 people is the last simulation. I believe that's the one that shows you 647 people were infected out of 2,000, but it was sort of spread out over, I guess it'd be 80 days, and no more than 60 people were infected at one time. So that's one particular scenario. And what you would do is, you'd say, hey, I wonder if I changed the vaccination rate and I made it a little bit higher. Or so let's make it like 2%. So this would be, because I have to divide everything by 10. So it is because of the tenth of a day time steps. You have to be careful a little bit. Maybe I want to increase. Maybe I'll increase the. Maybe I'll make it so that you could say my beta value is a little bit higher. So that's going to make R0 a little bit higher. I think it'll be closer to 2. So I have a more infectious disease, but my vaccination rate is higher. Okay, so you tweak variables and then you just see what happens, and you just have some fun with it. If anyone wants me to share this and play around with it, you can, and I can go in more detail, but it's kind of fun. And then there you go. There's another simulation. And while we wait for this one to load, maybe I'll go back into, I actually did 4 simulation sets, so I'll briefly talk about these, and then we'll look at the results of what I just ran. So I also looked at vaccinating throughout the pandemic, so kind of like what we're doing now. And, vaccination between 0 and 2.5%, I ran like different, I ran like different simulations under, I think, like 0.5 degree percent increments. And I also compared it to pre-vaccination. So if you're lucky enough to get the vaccine before your particular town is infected, then which wasn't the case for COVID, but then I compared that to that as well. So I looked at initial infections, either 2, 5, or 10. And then I recorded summary statistics as I always do. The question I was kind of interested in was, how does the simulation average compare to what we would do, what I call like the theoretical curve? And remember, like, the fade out actually has a big deal with that. But I found that even if you account for the fade outs, I believe in some cases the deterministic model was still over predicting what would happen. So I'll have to review my work to confirm that. But just so that was sort of the idea. And then, I've got a table of scenarios. I tested all of those and then some. And then the last one that I did was, if you have a vaccine program and you decide you're going to do it for this many K amount of days, compared that to no pre-vaccination there was no pre-vaccination. I compared like different vaccine programs, kind of like what we're doing now. Like we're vaccinating like in Ontario, maybe like, I don't know, 1% per day. I haven't really got the exact numbers, but we've got a steady rate going now. Initial infected was, I think, 5 most of the time for that one, and vaccine efficacy was stated at 0.7, because I've realized that it didn't really make much of a difference if it was like 0.7 or 0.6, and those are reasonable values. I looked at, I graphed the final size of the epidemic versus the number of days vaccinated. And I looked at like the 5th percentile of the simulation versus the 95th percentile of this simulation. And I also compared that to the deterministic model. And I also, like I did before, I looked at like a time series plot for like a couple of different cases, which I think I used spreadsheet for that, but you can also do with R. It's just not that pretty. Let me just get that simulation up to finish things off here. Okay, so I got to press enter on the histogram, and then it will tell me another histogram. So, okay, it's very similar. I didn't tweak things too much though. I think I increased the vaccination rate a little bit. So I guess I think the epidemic size, I don't remember. I think the epidemic sizes are a little bit less. No, that's about this. Actually, they're about the same, because I also increased the infection rate. So actually those two things sort of canceled out, I think. And if we look at one simulation in particular, I could do that by doing plot I, and it will plot one simulation. And yeah, very, very similar scenario. So all I changed is I made the disease more infectious, but I also made the vaccination rate increase. Those two sort of counterbalanced. But again, you could tweak and you can have some fun with it, and you could see, hey, what happens. So I hope that gave you a little bit of a taste of like what the goal of this is, also like give you a taste of what goes on between mathematical models. You might be hearing on the news, oh, the models say this, the models say that. What actually goes into I know mine is like very simple, and I'm not by means an expert, but I have an idea of what goes into the simple model. Of course, the models that the big guys are doing, they're going to include things like age structure, or like clusters. So accounting for, we're not just aimlessly running around, but there's sort of a network structure. They may account for many other variables that I didn't account for here. But at least it gives you a little bit of taste what goes on behind the scenes. So hopefully you found that somewhat interesting. I'll stop recording here, and before I let you guys go for today,